All right, so sum or difference. So we are finding two angles you can add together or two angles you can subtract to get you to 15. So what is one example of angles off the unit circle that if you were to add or subtract them, you could get to 15? You could, I don't know if 15 degree angle, I don't think 15 degrees is on the unit circle. Yeah, you could do 45 minus 30. What's another one?
360 minus 345.
360 minus 345. What's another one? What about 150 minus 135? So whenever you do these problems, you always have options. There's like multiple different ways you can do it. And depending on which angles you choose, your answer could look slightly different. So if you compare it with somebody else, don't automatically think you're wrong if it's not perfectly matching. That's why we have our calculators today, so that we can compare the decimals, because even if the answer looks different, the decimals would be the same. And so it's a good way to check your answer. All right, of the three options, which one do you guys want to do? The first one. Okay. So we're going to do sine of 45 degrees minus 30. So if we look at our sheet, you have to be really careful because instead of writing 6 formulas, I only wrote 3. So if we're doing sine minus, the minus is on the bottom, and so that means that we use the one on the bottom. Okay? So for sine, if this is minus, then this one's minus, but you'll notice that for cos, the signs are opposites. If you're adding, then it's a minus in between. If you're subtracting, it's a plus in between. And then tangent is kind of a mixture of the two. All right, so just be careful. Some students last period were getting problems wrong just because their signs were off, okay, not because they were plugging things in wrong. So for this one, we're doing, we said 45 minus 30. We're doing 45 minus 30, so it's a minus problem, so we're going to use the minus version. Do you guys want to keep it in degrees, or would you rather look for pi fourths and pi sixths? Yeah, I'm a little bit more used to the radians as well. So we'll call this sine of pi fourths minus pi sixths. And so that means that this is your alpha and this is your beta. Okay? And so the reason I'm writing it that way is because that's how the paper has it listed, is sine alpha and beta. Okay, so first we write sine alpha cos beta, and then we have minus cos alpha sine beta. So sine alpha is pi fourths, cos beta would be pi sixths, and then minus cos alpha, so cos pi fourths, sine beta, so sine of pi sixths. And then we'll go ahead and get our unit circles out. So we're looking for sine of pi fourths. You're close. Yeah, root 2 over 2. And then cos of pi 6. Square root 3 over 2 minus pi fourths. Root 2 over 2, cos of pi fourths, I meant. And then sine of pi 6, 1/2. All right, so the first fraction, 2 times 2 on the bottom is 4, so it definitely has a denominator of 4. If you do root 2 times root 3, what do you get? Root 6. So we have root 6 over 4 minus, again we have over 4, and then we have root 2 times 1. Root 2, and so we can write this as one big fraction that's over 4. Root 6 and root 2 are not like terms, so you can't combine them. You literally just write root 6 minus root 2. And so that's the answer. Now, there are multiple different answers we could get that would be different combinations of the root 6s and the root 2s with different positive and negative signs. So the best way to check your answer and compare it with maybe my answer key or compare it with somebody else is to type it in the way that it looks. So here this says sine of 15 degrees. So before I hit the sine button, I would have to switch my calculator into degrees so that it matches the problem. And then I would type sine of 15 degrees and get my decimal. And then I'm going to compare that with this answer. So if you want to type it in like this, you just have to hit alpha y equals so that we can type it in like that fraction. And then square root 6 minus square root 2 over 4 is the same decimal, so I know I did it right. Okay. So that's going to be the best way to check your answer for today. I do have an answer key up, but unless you chose exactly the same numbers as me, your answer could look a little different. Okay. All right. So there's a sine problem. We also want to do a tangent problem. So let's go ahead and jump down here. These ones are in terms of radians. I don't know about you, but it's hard for me to think about adding fractions to 11/12 or subtracting fractions to 11/12. So what I normally do is I convert it into degrees. So 11 divided by 12 times 180 is 165. So I would say this is the same thing as tangent of 165. And what are some numbers on the unit circle that add or subtract to 165? $135 and 30. $120 plus 45. What about 210 minus something? What is it? 45. 210 minus 45 would get you to 165. So you don't necessarily have to do adding or subtracting. You could do either or, whichever one you want is fine. All right, so for these, there's a little bit of strategy involved with tangent, because sometimes when we do tangent, we could get root 3, right, which is pretty easy to work with. Sometimes when we do tangent, we get root 3 over 3. Which, if you guys remember from the video, the root 3 over 3 made the problem a little bit more difficult. So what I like to do with tangent is come up with a few different options, and then if I can avoid using a root 3 over 3 for tangent, then I can make the problem easier for myself. Does that make sense? So if you remember yesterday, I did the same problem twice, or whenever you watch the video, I did the same problem twice, and I showed you that it could be easier or more difficult depending on what you choose. So 135, if you look at your unit circle, that's the same as 3 pi fourths. And we know that the fourths are always 1 or negative 1. So pi fourths, 3 pi fourths, 5 pi fourths, those are always nice, right, with tangent. So we're not really worried about that. But if we look at tangent of 30 uses the point root 3 over 2 for x and 1/2 for y. And what happens when you do y divided by x? The tangent is what? It's root 3 over 3, right? So this is one of the more difficult ones, so I don't want to do that because I'm feeling lazy. Okay. Tan of 120, that's the same as 2 pi thirds, and so that's the point negative 1/2 positive root 3 over 2. And what happens if I do y divided by x? It's negative root 3, right? Root 3 over negative 1, so negative root 3. So this would be a good one because it's not the root 3 over 3 fraction. It's not that you can't do it with this one, it's that it just becomes a more difficult problem, and if you're feeling lazy, then you might as well avoid it. Okay? So let's go ahead and we'll do this one for this particular problem just to make our lives easier. So the strategy with tangent is to avoid the radians that have a 6th in them don't do tangent of pi 6 or 5 pi 6 or 7 pi 6 or 11 pi 6. If you use the tangents that have the thirds in them, those are the easy ones. Pi thirds, 2 pi thirds, 4 pi thirds, 5 pi thirds. So if you can use those as part of your problem, then it makes it easier to get the answer. It's not impossible the other way, it's just kind of a headache. That's it. So I'm going to go ahead and write this out. I have tan of, I'm going to do alpha plus beta. I know that's pi fourths, and then 120 is pi thirds. So pi thirds plus pi fourths is going to get us to 11 twelfths. Here's my alpha, here's my beta. So if I look at the tangent formula, it says if I use plus in here, then for the top of the fraction, I should add them together. For the bottom of the fraction, I do 1 minus the 2 multiplied. Okay? So for the top, I'm going to do tan alpha, which is pi thirds, plus tan beta, which is pi fourths, divided by 1 minus tan of pi thirds times tan of pi fourths. Nobody corrected me, it's 2 pi thirds. 120 is 2 pi thirds. Don't worry, I figured it out. Did anybody notice that? You noticed? You guys were just blindly trusting me. You're like, she's the teacher. She's never made a mistake ever before, so. Yeah. All right, so tan of 2 pi thirds is what? We already did it. It's negative root 3. Negative root 3 plus tan of pi fourths is 1, divided by 1 minus negative root 3 times 1. So on the top, we have negative root 3 plus 1. On the bottom, we have 1 minus, and then this, of course, when you multiply, it would just be negative root 3. And what happens when I have a minus minus? Plus 1 plus root 3. Okay? So to check my answer, I'll go ahead and do the original problem. So I'm going to turn my calculator back into radians because this said 11 pi twelfths. And if I do tan of 11 pi twelfths, that gives me that decimal. And then if I type my fraction in, I have negative square root 3 plus 1 over 1 plus square root 3. And I have the same decimal. So you'll notice because all of these numbers are coming from the unit circle, you're going to notice that your answers are feeling very repetitive. If you get an answer that's brand new and unique, you probably did something wrong. So anytime you're doing a sine or a cos problem, you're going to have lots of root 6s and root 2s and over 4. For the tangent problems, you're going to have a top and a bottom of a fraction that look kind of like this with root 3s and 1s in them, and maybe 3s, okay, depending on how you do it. All right, and then on the back of this, it gives you a couple proofs to do, and they're fairly similar to the one I did in the video. So if we need to, I can help you guys with some of these. Okay. So your goal for right now is to do the first page front and back completely, every single problem, and then later on towards the end of the period, I'll start going over problems for the next page. Okay. All right. Go ahead and get started on that. Okay, so I want you to have your trig identity sheet in front of you because we're going to add something to it. So the formulas that we're going to look at now are the double angle formulas and the half angle formulas. Because this semester is cut a little bit shorter, I decided not to go over these. So these work the same as what you were just doing. If I wanted you to find a 22.5 degree angle or sine of a 22.5 degree angle and I wanted you to give me the exact answer, you would just do sine of 45 divided by 2 because 45 divided by 2 is 22.5. and then you could use your unit circle and give me an exact answer using the formula. Okay, so so these would work the same. Normally I would have spent a day going over some of these, but and then the same thing with double angle, but we don't have time to cover everything, and this is not likely to be on the final exam. And if you don't have this, it won't affect you too much for calculus. So what I did want to do though is I found some proofs that use these formulas, because these formulas do seem to come up in calculus, and so it would be nice for you to have the practice with the proofs of like substituting things out so that you're a little bit more familiar with them if you choose to take calculus. So before we start to use these formulas right here, we're going to come up with a couple alternate forms. So what I would like you to do is take this sheet and flip it over, and you're going to write this on the back, but I already wrote on the back of mine. So I'm going to do it on notebook paper this time. So what you're going to be writing on the back is, you're going to say cos of 2 theta equals 2 cos squared theta minus 1. So I'm taking one of these double angle formulas and I'm going to rewrite it in an alternate form. Okay, so if you notice here, sine of 2 theta only equals one thing, but cos of 2 theta has 3 different things that you could substitute in for it, and all 3 of those come in handy sometimes, okay? And then tan 2 theta has a substitution, but to be honest, I've never really used that one, so you can kind of take it or leave it, I guess. All right, so cos 2 theta, one of the substitutions you can make is 2 cos squared minus 1. And what we're going to do is we're going to isolate the cos squared. So the first thing I'm going to do is add the 1 to the other side. So that gives me cos of 2 theta plus 1 equals 2 cos squared theta. And then second, to get the cos squared alone, I'm just going to go ahead and divide the whole thing by 2. So the alternate form that we end up with is we say that cos squared is the same thing as this, because those 2's canceled out, and they typically don't write it in this order. People typically write 1 plus cos 2 theta divided by 2. So based on the work that we did on Friday, if I was to say what's an alternate thing you could plug in for cos squared, most of you would say 1 minus sine squared, because we've done that over and over. Oh, it's a cos squared, replace it with 1 minus sine squared. That's like been repetitive. When you get into calculus, this is going to be the thing that you're going to want to replace cos squared with most often. So if you were to ask my calculus students what could you replace cos squared with, most of them would say 1 plus cos 2 theta divided by 2, because this is what we've done. The reason that we use this in calculus, we call it a power reducing formula, because here you have a cos that's squared, and here your cos is not squared. And so sometimes in math we want to not have an exponent of 2, we want an exponent of 1, and this is how we use it in calculus, okay? So just wanted you guys to see where that comes from. This is actually used on that worksheet. So go ahead and put a box around this. We're going to want to save that. And then we're going to do the same thing with one of the other cos of 2 thetas, so the other double angle formula for cos. So I'm going to say cos 2 theta equals 1 minus 2 sine squared theta. And so here we want to solve for sine squared. So just like before, I'm going to go ahead and minus the 1 over. So I'll go ahead and kind of manipulate this one so it's in that order, the way that this one is. So I'm going to say negative 1 plus cos of 2 theta equals, and since the 1's went away, I now have a negative 2 sine squared theta. And then I'll go ahead and divide by negative 2 and divide by negative 2. And so we would cancel those, and so we'd say the other form is that sine squared theta equals, and what they do here is they just take a negative out of the problem, so that would make you change all of the signs. So they make this a positive 1, they make that a minus, and they make that a positive. And as long as you do it to everything, it's okay to do that. So you'd say 1 minus cos 2 theta divided by 2. And so that's the other one. So you'll notice they're very similar. So on your sheet, when you start to look at these proofs that I'm asking you to do next, you'll see that these show up in a couple places, like 1 minus cos 2x. They don't all have the over 2, but they're pretty, see, like 1 minus cos 2x. So you'll see that fairly often, and the reason for that is because these are pretty common to use in this way. Okay, so let's go ahead and start off by looking at number 1 on the sheet. Now, there's a lot of white space on here, so if you want to just do the problems on here, you could, and you could do them on the back. I'm not going to have you do all these problems. There's 16 of them total. I'm going to have you do 5 total, in addition to the 2 that we're going to do together. All right, so you're going to be doing 7 at the, as a result. But we're going to go ahead and do 1 together. This one says cos 2x over 2 sine x cos x equals 1 over tan 2x. This is number 1. Yep. And I would say, so again, we always look at the more complicated side. It's a little bit easier to do that. And so for number 1, I think the left side looks a little bit more complicated. If you compare the left side with the right side, you can see that the right side has that double angle there. So it's saying not just tan of x, but it's saying tan of 2x. And so when I compare that with the left side, that means I'm going to go ahead and leave the cos as cos 2x. I don't want to substitute something else out for it because then somehow I would just have to switch it back into a double angle. So I'm going to leave the cos like that. So that means I'm going to be looking at 2 sine x cos x. And for all the problems on this sheet, you're going to have to use at least one of these formulas. Okay? So if we look at this, what do you guys think we could do to the bottom? Change it to sine of 2x, right? So the cos 2x is going to stay the same. The bottom is going to become sine of 2x. And if I have cos over sine, what does that remind you of? Close, not quite tangent. It's cotangent, yeah. So this is actually cotangent of 2x. And what do we know about cotangent? It's the same as 1 over tangent, yeah. So this is the same as 1 over tangent of 2x. Okay, so that problem is done. Okay. Next, we're going to go ahead and do number 2. Actually, I'm going to write this down. All right. So number 2 says cos squared times 1 minus cos of 2x. Now, if the 2x sitting like that kind of messes with your brain, I don't know if it does, but it makes my brain feel weird, so I like to put parentheses just to show that all of that is the angle, and that seems to help me make more sense of it. So equals sine squared 1 plus cos 2x. Okay, so if you look at this, does one side look more complicated than the other? Yeah, they look about the same, right? They're kind of similar on each side. So it doesn't matter which side we work on. What do you guys want to do? The left. Okay, let's look at the left. So if you compare this, do you guys notice how similar these are to the formulas I just showed you? Those alternate forms? Because we have a 1 minus 2 or 1 minus cos of 2x and a 1 plus cos 2x, and that's like the same as these. So when I see that in the problem, that gives me a clue that maybe when I see this cos squared, I should replace the cos squared with this. And the reason I was thinking that is because I noticed that those are very similar and that the problem itself had a cos squared and a sine squared, okay? So what I went ahead and did is I took the cos squared and I'm going to write 1 plus cos 2x over 2 multiplied by the 1 minus cos 2x. Okay. And then what I noticed from here is that I want this to stay, but just the top. I don't want the 2 on the bottom to stay, but I do like it when the top stays. Does that make sense? Because that's on the right side. So I'm going to think of this as 1 plus cos 2x times 1/2. So all I did is I said this divide by 2. I'm just going to move it over off to the side. Because I know I want to keep this, but I don't want to keep that 1/2. I'm going to want that 1/2 to go away. And then I have a 1 minus cos 2x. So right now in the problem, this and this are the same. And that means I need to get rid of this. So what do you guys notice if we look at the two problems we just rewrote? Do you see anything? So this right here, it doesn't quite look exactly the same. The 1/2 is in the front instead of having a divide by 2 over the whole thing. But this is technically the same as this. So that means that what I can do is I can take this part right here and just write it as sine squared x. And that means I'm done with the problem. They're just kind of written in backwards order. So in theory, I guess I should switch that one, but... Okay. So homework for tonight, in that packet, first page, front and back, completely done. All the stuff over sum and difference formula, completely done. Okay? On the very last page, the one that had the double and half proofs, we just did 1 and 2, so you should definitely have 1 and 2 done. And then you pick 5 problems to do. Okay? So I'd say try number 3. If you get stuck, move on to number 4. So if you get to a problem and it seems difficult to you and you don't want to do it, that's fine. I will be putting the answer keys online so you can check them if you get stuck on a problem. But of those 16 problems, you have 14 left, because we did 1 and 2. Of the 14, I want you to do 5. All right? Reasonable? Okay.